Welcome to lesson 4 of permutations and combinations. We are now going to introduce this idea of permutations. Now, in truth, I don't use the idea of permutations very often. I basically use the fundamental counting principle. Almost all the time because I can work through that, or I use the labeling principle discussed earlier. Right? To me, both of those are maybe more easier, but they're the same principle, they're the same concepts as what we're talking about here. Actually, I don't even use that very often in this case. However, we do have to talk about what is a permutation, what is the formula for a permutation, what is the notation for a permutation. Now, permutation is a big 50-cent word for arrangement, and that's why I use the fundamental counting principle so much, is we are arranging things, I tend to go to there. How many three-letter arrangements of the word money are there? Well, that's easy. 5 times 4 times 3. How many two letters? 5 by 4. Now, that's our fundamental counting principle. It's nice and easy, not a real worry that you have to do with this. How many different, what you can look at this as, this is 5 by 4 by 3 by 2 factorial over 2 factorial. Over here, we have 5 by 4 by 3 factorial over 3 factorial. Now, why would I want you to write it out like that? Probably not going to. But this does lead us to this part about permutations that we want to look at. We can now write these guys as 5 factorial over 2 factorial and 5 factorial over 3 factorial, respectively. Now, what this leads us to is an idea. Now, this here is 5 factorial over 5 minus 3. Where the 5 is the number of objects, the 3 is the number of objects we're arranging. Over here we have 5 factorial over 5 minus 2 factorial. Again, the 2 is the number of objects that you're arranging. So this leads us to our formula, which is going to be n factorial over n minus r factorial. So this notation, we're taking 10 objects, arranging 3 of them. How many ways could we do that? Well, fundamental counting principle says we can go 10 times 9 times 8. The permutation notation, that would be 10 factorial over 7 factorial, which we would get by going 10 factorial over 10 minus 3. Now, a couple ways that I say this. The proper way to say this is n perm r, and then I say n pick r because I've always associated pick with arranging objects. I know, strange, but it does work out. So this notation here is given to you on your formula sheet, and we will work with it. N and R must be whole numbers, because otherwise we could not do factorial. Our definition of factorial is only just the numbers have to be whole, otherwise our definition doesn't work. And then we also have to have n greater than r. So if I say 3 pick 5, and we go back to what this means is how many arrangements of 5 can I make from 3 objects? Well, I arrange the first guy, arrange the second guy, arrange the third guy, I reach back into the bag, there's no more objects to pick. That's why this makes absolutely no sense. There is no way to take 5 objects and arrange them if you only have 3 to begin with. Now, n pick 4, or 10 pick 4, I should say. So this means arranging 4 objects from 10. Go ahead and do that with the fundamental counting principle if you want. If I'm doing this with this notation, 10 factorial over 10 minus 4 factorial, 10 factorial over 6 factorial, we can cross that off. We have 720 times 7, so 5,040 ways. Again, that's going from here to here is just math, and we all can do that. So, as I said, fundamental counting principle, if I don't have the 10 pick 4 and I just say arrange 4 objects from 10, or I say how many 4-letter words are there can be made from this 10-letter word, we can do fundamental counting principle, which is just this, but this is how we get there using the permutation notation. Now again, we're back with our English, because it's a subject in high school that doesn't have any repetitions. If I want to take how many arrangements of the 2 letters are there from the word English? Well, we have 7 objects, 7 letters to pick from, 7 objects, and we're picking 2 of them, or arranging 2 of them. Again, many of us will just write 7 times 6, because that's what 7 pick 2 works out to be. But there it is in your permutation notation. There it is using your fundamental counting principle. 5 letters, 7 pick 5, 7 times 6 times 5 times 4 times 3. Again, this is our fundamental counting principle, multiplication principle, where this is our notation for permutations. Now, how do we do this when we have another problem? We got the word brains here, 6 letters, but we want the vowels to be together. So before we go to answer any of the other stuff, we have to take our problem and see what we can do. We got to get the letters together, or the vowels together, I should say. So I'm going to make up a new Scrabble tile that's consisted of A and I, our 2 vowels. That leaves us with B, R, and S. So if I was arranging, now I've got 5 objects. So how many arrangements? Okay, so we are doing the entire 5 objects. So we're arranging all the different letters. So this would be 5 pick 5. 5 objects, we're picking 5 of them. But, again, did I say A and I had to be in that order? No, I could have it in this order, or I could have it in this order. So now we're going to say that there are 2 ways of arranging the vowels in there. So now we have 5 pick 5 times 2 pick 2. Again, fundamental counting principle says 5 times 4 times 3 times 2 times 1 times 2 times 1, because of the different ways to arrange these. If I was talking about 3, there would be that we would have more there. Vehicle plate questions are relatively common. A vehicle plate consists of 2 different letters followed by 4 different digits. If the numbers I, O, Y, and Z are not used, how many different possible combinations, or how many different license plates are possible? Now, here we basically have to decide can I repeat 2 different letters and 4 different digits? That means no repetition. If I pull a M out of the bag for the first letter, I put it aside. There's no more M's in the bag. Okay, if there was allowing repetition, I could put the M back in the bag. So a fundamental counting principle are letters. We have 22 letters for the first one, 21 for the second, because there are 26 letters and we've taken these 4 out. And I'm going to multiply that by there are 10 different digits, then 9, then 8, then 7. Because I can't do repetitions, I'm allowed to do permutations with this. If I said repetitions were allowed, the only way you can do that is using fundamental counting principle. The permutations, well, here we have 22, pick 2, 22 letters, we need 2 of them, putting them down in order, times 10, pick 4. 4 of the 10 digits need to be placed down. I don't care, in a question, I don't really care which way you do this. I just want you to be able to recognize that this is the answer, because we have to use these permutations. What happens when I give you permutations and I want an equation? Now, I hope I fixed this one already, because I know in the past this is not going to be solvable, but I think this one is. Basically, n minus 1 pick 2 is equal to 90. Now, that's just annoying. Well, here we have a formula. N pick r is equal to n factorial over n minus r factorial. So I'm going to take that and I'm going to replace this with the form of that. So our top guy is n minus 1 factorial. Our bottom would be n minus 1 minus 2 factorial, and I'll keep the 90. So now I've got n minus 1 factorial over n minus 3 factorial is equal to 90. Well, we've turned it into where we've got factorials. We've got this ugly, but we still have some uglies. Well, we have a factorial over a factorial. Take the largest one, expand it. And I can see that those guys are going to cross off, leaving us with n minus 1 times n minus 2 is equal to 90. I recognize that this is a second degree equation. The only way to solve second degree equations is to get everything to one side and factor. So I've got n squared minus 3n minus 2 minus 90 is equal to 0. And then we would factor that. N squared minus 3n minus 92. This is where I don't think it's factorable. Numbers that multiply to negative 92 and add to 3. 1 and 92. 2 and 46. 3 doesn't work. 4 doesn't work. 5 doesn't work. 6 won't work. This is why I don't think it's going to work. 7 doesn't work. 8. 8 won't work. And 9 definitely doesn't work. So right now I can't solve this. The problem is wrong. The process was correct. The problem is wrong. I can't solve this, but I would look to see to factor this if I could. So That's something I have to fix in my notes. The same thing down here. We're going to end up, tells you to solve a third degree function. What is that function? We're not asked to solve it, we're just asked what is that function. So again, here we have this kind of ugly notation. This one doesn't work either, does it? I'll just skip this one because it doesn't work. Really got to fix these notes. Sorry. So going back up to here, this is the process that you would use to solve it. Again, if it's factorable, you factor it. You can't use the quadratic function or quadratic equation for this because we know that our answers have to be whole numbers, and that doesn't work in this case. Quadratic function rarely gives you whole numbers. So that is the lesson for today. It's a very short one on permutations. I will go over the homework with you and during tomorrow's lesson. There's your homework. You can find that online. I shall see you later.